lecture. We are getting very close to being done. So for many of you, you are done.
Yes, we are done.
Unless, of course, you come back for lecture.
No.
No.
No here, no here.
Why not?
Arizona.
I say why not? You guys should. And the other thing I'm going to ask you guys is, did you learn anything? You have learned something this semester?
Yeah.
That's the agenda. So yeah, the final will be posted probably Friday after the competition, and then you'll have 1 week to work on the final and submit it on Canvas. All right, so we've been talking about this idea of smooth motion profiles, or making sure we have smooth motion profiles, so that we don't have those discontinuities. And so we talked about the ideas of what if we were to create higher order polynomials to express the positional displacement relative in time to those motions. And we can do that very simply using an nth order polynomial of the time derivative as our expression. So what that means is that we're looking at finding these coefficients for each one of these time variables. And so this would be a third order polynomial, but we have to figure out what these t's are, or these c's are. And then to figure out what those c's are, we need to know some initial conditions. And so we can define these initial conditions through this vector right here. So here's our initial position, our initial velocity, our final position, and our final velocity. And then using the equation of motion to the whatever order we're using, we can come up with what these are going to be. So what is TF? So this is going to be a certain value. Here's going to be a TF squared, right, with the 3 as the coefficient in there. From there, we can just do some very simple linear algebra to solve for our coefficients matrix, and we can do something that looks like this. So let's go ahead and look at an example of this. I'll go ahead and stay in that same mode. So this is the one from the book. I'm just going to go through the book and explain and expand upon the example in the book at the same time. So we have our initial theta at time initial is going to be our C naught, which is going to be set to 30 degrees. And by the way, we're going to run this example. We're going to say 0. Time is going to be defined from 0 to 5 seconds. We want our final position, which is going to be defined through C naught plus C1 up to 5 seconds, so our final. So again, this is T final, so we can put a 5 in right here, plus C2, 5 squared, plus C3, T cubed, or 121. Okay. That final position, we want to be at 75 degrees. So that's our initial condition. Our initial velocity is going to be C1, which is going to be set to be 0. And our final velocity we want to come to a rest. And that way we can just describe that through the polynomial equation of C1 plus the derivative, so basically we take our derivative of theta to find theta dot. So we're going to have that 2 times our TF, let me just say C2 here, times C2 times our TF, which is going to be 5. Then we're going to have 3 C3, and then we're going to have TF squared, or 25. And our final velocity is going to come to a rest, so we want that to be 0. We don't have to have it come to a rest. It could have another velocity. As we go in from one point to another, it could actually have a transition. So we could say, hey, actually I want to be 5 degrees per second. So we're going to solve for 5 degrees per second. Okay, so we have a variety of initial conditions, and I can solve for them using any methods that we want, but we can also just put them into what we have. So we're going to have our M matrix minus 1 is going to be times theta. And we're going to get our C vector that we see right here. So when we do that, very simple calculation, we're going to find that C is equal to 30, 0, 5.4, and 0.72. So those become the coefficients. So using these coefficients, then what we're able to do is we can compute both theta of t and theta dot of t for any t. So in other words, our equation of positional displacement is theta of t becomes 30 plus 0 t plus 5.4 t squared plus 0, sorry, minus. This is supposed to be minus, my apologies, that's a minus. So minus 0.72 t cubed. I can also compute my theta dot of t, which becomes twice 5.4, so we're going to get 10.8 times t, and then we're going to 3 times the 7.2, which is going to be 2.16. And it also means I can actually take the second derivative of theta. I can find out my accelerations at any point in time. And so I would see this as be 10.8 minus 4.32. And so we see that we have a linear acceleration from this perspective. We have a constant jerk. If we're to look at the jerk at that point as well. So here's my offset. Right, that's my offset acceleration. That's the acceleration that I'm starting at. And then, of course, this part right here is nothing more than my slope. And so what we can do is we can compute theta, say at 1 second, at say 2 seconds, 3 seconds, 4 seconds, and 5 seconds. Actually, I think I only have 1, 2, 3, and 4. Because 5 we already know, it's our final position. We said we're supposed to be 75, right? So we can just write that down here. So 75, we started at 30. Actually, that should be theta 0 was 30. So again, you put 1 second in, and we find we're going to get 34.68. And then we're going to get a 45.84, 59.16, and 70.32. So if we look at these deltas, it's got 4, then we went to 9, went to a pretty big number, and then we kind of like backed off, right? In fact, if we look at our theta dots, so our theta dot 0 was 0, theta dot at 1 second, when we put that computation in, we're going to see it's going to be 8.64 degrees per second. And by the way, this is going to be all in degrees, right? Theta dot 1, the velocity at 2 seconds is going to be 12.96 degrees per second. Theta dot at 3 seconds is going to be 12.96 degrees per second. So we can see between 2 and 3 seconds that we're peaking and then we're coming back down. So we've increased our velocity from our starting velocity. So we have 0, then 8. So again, this is the amount of velocity that each joint has, or this particular joint has. Theta dot at 4 seconds is going to be, as you would expect, 8.64. It's on the other side of that parabola. And then theta dot at 5 seconds, as we defined it, was going to be 0. The acceleration is pretty darn simple. It's just going to be that line. We don't really need that. We could compute it if we wanted to. Any questions so far? So now we can actually graph it. So if we graph it, and I can do, this and go down. Actually, you know what? I don't need quite that much y-axis. So let's do 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. And so 1, 2, 3, 4, 5. And let's just go ahead and make this 25, 50, minus 25, minus. And actually go up to 70. I'm going to move him over here. Theta dot at 5. Okay, so our position, we started off at about 30 degrees. And then at 1 second, it was 35 degrees, right? So 1 second is, I don't know about right here. At 2 seconds, we were at 45 degrees. So here, at 3 seconds, we're at 60 degrees. At 4 seconds, we're at 70 degrees. And then 5 seconds, we're at 75 degrees. So we see something that looks like this, which when we look at that, that's a cubit all day long. So that's the path that's being implemented. It's the trajectory when we look at the duration. We look at the velocity, we're 0 at initial and we're 0 at 5. We're 8.6 at 1. So let's just call it, I don't know, a third of the way up, right? So here and here. We are roughly 15, so let's just call it here and here 3. So we can begin to see this parabola looking something. So this is our theta dot. Then our acceleration, we start off when t is equal to 0. So we just go ahead and write the equation of the line for acceleration. So then theta dot, double dot, is equal to 10.8 minus 4.3. Right? So at time t equals 0 means we're going to accelerate at about 10.8 degrees per second per second. Then we're going to have a constant slope. We're going to cross over at this peak right here. Right? We take the derivative. We know that that's going to be our 0 point. But we're going to see that part right there. So we have a positive derivative, and we have a negative derivative in here, and that's what we see right here in that slope. So this becomes our theta double dot. So the final point the acceleration is going to be minus 10.8 degrees per second. Now, that's the first motion. You know, sure know how to do this on the exam. I'm going to give you a homework problem today that's going to have you practice these things, okay? This is a third order polynomial description. That's the first trajectory. It moves from here to here. Now, what we want to do is actually have, after the 75 degrees, we'd like to see it go to 105 degrees for its positional displacement. So after the initial displacement from 30 to 75 degrees, the joint must move to 105 degrees in 3 seconds. That's what's coming out of the path, trajectory, and from the inverse kinematics. Remember, the inverse kinematics is going to give us our destinations. Then the velocities are going to be defined through everything we did in Jacobians. So we have to define the initial conditions. So actually, let me say this, find the new coefficients. For the next function. So again, we define the initial conditions, much like we did before. So again, theta dot, or theta of t, we really don't need to write, we already know what this is. It's going to be c naught t plus c naught plus c1 t plus c2 t squared plus c3 t. And just like we had before, again, theta dot is going to be equal to c1 plus 2c 2t plus 3c3 t squared. And again, we can now we want to actually look at the acceleration. So our acceleration of t is we're going to see 2c2 plus 6c3. So far, so good. So these are our equations. Let me say what you next do for the next motion. We are also going to say evaluate with Excel. And then we're going to go ahead and we're also going to draw the motion profiles. i.e. position, velocity, acceleration. Everybody good so far? All right, so again, this is now our next sequence. So at t initial equals 0, that implies that our theta initial is going to be 75 degrees. Our theta dot initial. So we moved from 30 to 75. We stopped, we started, we accelerated to the velocity, and then we came down, right? We ended at a 0 velocity. So that means our initial velocity is going to be 0 for that next phase. Our theta final is going to be 105 degrees, and our theta dot final is also going to be 0 degrees per second. So now find C. So again, I have my initial conditions. C naught is 75. I can say that C1 is going to be 0. C2 is going to be 10. C3 is going to be minus 2.2. So using the process from before, this is what we're going to find. I encourage you guys to do that on your own. I'm skipping that step because I already did. Is that fair for all of you? Otherwise, we just take too long. But we're going to find that these are the parameters that we're going to find for C1, C2, C3, C0. So what that really means is my equation now is going to be defined as theta of t is going to be 75 plus 10t squared minus 2.2 e cubed. Theta dot of t is going to be 20t minus 6.66 t squared. And theta double dot of t is going to be 20 minus 13.32 t. Now, what we notice here is our acceleration is minus 20. What was the acceleration we had before? Exactly. Theta double dot final of t final. Come on, erase it. Or just scribble it out. Theta of t final prior was equal to minus 10, right? So what we're going to see is between segment 1 and segment 2, there is a large delta acceleration. Large delta accelerations are bad. Why are they bad? Because they require a lot of current, because they require a lot of torque potential. So we're going to go ahead and graph this, but it's not a good idea. And it turns out we could think of think of that 75-degree, theta equals 75 degree as a waypoint. From 30 degrees to 105 degrees. So if we draw our graphs again, so here we are at 5, 6, 7, 8. So this was before. So this is going to be segment 1, and this is going to be segment 2. And 1, 25, 50, 75, 100. Let's call that 105. So we saw what it looked like right here, right? So we have that same graph. Now it's not going to look as pretty the second time, I'm sure. Bear with me. We were at 30 at 1. Let's go back. 30 at 0, 35, 45, 60, 70, 75. Not bad, I guess. And then from this next one, it's going to go up to 105. We're going to see our acceleration, velocity is going to do this. Come to 0, and then it's going to go up like that. We're going to see our acceleration do this, and then it's going to jump to here and go down like this. And so this becomes the problem. Okay. We have a large potential acceleration to manage because we had 2/3 orders. So if I have 2/3 orders causing this discontinuity and acceleration for my waypoints, let's be a little smarter about this, right? What could we do? There's 2 things we can do. Let's talk about one of them first. What is something we're able to do in order to alleviate that discontinuity? Because that discontinuity, this massive change in A is going to cause a massive change in the impulse, and that's going to have a massive effect of the force and the torques, as we saw in Lagrange. Right? Wait a second.
Really big acceleration.
What if how? Because that's a discontinuity, right? How do I avoid the discontinuity? When I was doing a second order, let's use a whiteboard for this one. When I was doing this, we knew we had a discontinuity, right? So how did we avoid that discontinuity? I went to a third order, right? And That's what we saw right here, just like that. So what do you think we ought to do to avoid the discontinuity here? Go to a higher order, exactly. In fact, we could go to a fifth order. Why not, right? So to overcome the large jumps in acceleration between stop and start at the waypoint, we can use a higher order poly, namely a fifth order. Okay. This seems pretty cool, yeah? I know your all definitions of cool and my cool are not quite the same sometimes. I accept it. You'll learn. But the Force Gump. It is Star Wars. I was thinking of actually starting off with the whole Star Wars theme right here for you guys, but I don't have time. Just imagine. Okay, so if I go to a fifth order polynomial to describe the position of theta, it's quite simple, right? So I could do theta of t as going to d, which is like do a sing-along right here, right? So I could do c naught plus c1 t plus c2 t squared plus c3 t cubed plus c4 t4 plus c5 t5. And therefore, theta dot of t, you guys tell me, is c1 plus 2c2 c plus 3c3 t squared plus 4c4 t cubed plus 5c, come on, stop, 5d4. And we can also say that the theta double dot is going to be what? 2c2 plus 6c3t plus 12c4 t squared plus 20, I put a c, a 5, c5, 5, plus 20 c5 t cubed. So far so good. And we can keep on going. Let's go to the third derivative of time. And that's going to give us 6c3 plus 24c4 t plus 60c5 t squared. And that's enough for what we're going to do. So obviously we need some initial conditions. And so theta, whoops, using the same one that we had before. Theta initial is going to be 30 degrees. Theta dot initial, I'm going to drop the t's if I can do that for you guys, is going to be 0 degrees per second. Our acceleration, we're going to limit to be 5 degrees. Okay. We're going to say you cannot exceed 5 degrees per second squared because I can't afford the torque. I don't have it in my motor. And then my final, so theta final is going to be 75 degrees theta dot final is still going to be 0 degrees per second. And my deceleration rate is still going to be minus 5 degrees per second squared. So I'm going to limit my accel, and I'm going to limit my decel. Using the same process that we had before of C's and M's, we can go through and just construct the equations, right? So we're going to have this matrix, or this vector, theta I, theta dot I, theta double dot I, theta F, theta dot F, theta double dot F. There's going to be some matrix, which are defined by our T's. And then we're going to have C0, C1, C2, C3, C4, C5. And you might be asking, hey, Dr. Bosco, why did we go to the fifth order? And how did I know how many initial conditions I was going to need? This size here, this is a square matrix, has to therefore be this size over here. So this becomes a square matrix. So therefore this and this becomes the same. Okay. This is a linear relationship. And so we can compute C becomes our N matrix times theta. So our C's could be, or is going to be, 30, 0, 2.5, 1.6, minus 0.58, and 0.046. So this is C5, and our C3 from before, if you recall, was, let me just put that parenthetical so you can see it, was 30, 0, 5.4, and minus 0.72. And so we see, as we add more, we see how these kind of changed up, right? These are the coefficients for C's. Am I, again, using these C's right here, we can construct our expression of theta time. So we're going to get 30. So we just put in the coefficients, right? Plus, there's no initial acceleration. I'm sorry, no initial velocity. 2.5 t squared plus 1.6 t cubed minus 0.58 t4 plus 0.0464 t. So at whatever time t I want to know where something's at, I can plug it in and find my theta. That's my position. Similarly, my theta dot of t is going to be 5t plus 4.8 t squared minus 2.32 t cubed plus 0.232 t4 And my acceleration at any point in time is going to be 5. So we're just taking the derivative. It's nothing major. 9.6t. Again, we're just writing the equations of motion. We write them all day long. So we're going to get 696 t squared, and this becomes 0.928 t cubed. So if we want to know the max acceleration, is finding the third derivative of t set equal to 0. Right. So we can find the third derivative right there. So we're going to get 9.6 minus, take the derivative of that one, we're going to get 2.2, or I should say 2 times, you can compute it if you want, 6.96 t plus 0.928 times 3 t squared. So this becomes our maximum acceleration set equal to 0. And solve. And so what we're going to find is this becomes our max acceleration. And solve. We're going to find one of them is bogus, makes no sense. The other one is going to be 8.704 degrees per second squared. And if we know our A, our max A, then that allows us to compute the force, which allows us to compute the torque, which allows us to define I max. Yeah.
I thought we already said earlier that our max acceleration and deceleration was 5.
That's our limiting value.
Oh, which are limiting, but not our max.
That's right. That's our start and stop. Yeah. So our acceleration graph will look like this. So we're going to start at 5 and end at -5. And we're going to cross over somewhere, say here. So we're going to see something that kind of looks like this. So this is going to exceed a little bit of 5, but starting and stopping at 5. So we're going to actually see theta double dot that we see right here. There's that transition point. That's going to be this equation that we have right here. So that's the equation of acceleration. Now, what if we didn't like to change, we still had too much acceleration, or we still had too much jerk, or too much derivative of jerk? What would we do in that case? Go to a seventh order, right? We could keep going all day long, right? So we could use a seventh order polynomial. However, it could become excessive. Because do we really, really care what's happening to our system when it's just flying Remember, this think of the airplane again, right? So the airplane takes off, it's cruising, it comes in for its landing. When it's cruising, do I really need a seventh order polynomial? I can get away with maybe a third order polynomial. So maybe I start with the fifth order, then go to third, and then come in for a fifth. Now the question is at what point, I'm starting off, do I transition his velocity accelerations? I'm going to transition from a fifth order poly to a third order poly. Right? And then I'm going to cruise along, and at some point, t minus some point here, I'm going to transition from a third order back to a fifth order for my landing. So I just have to figure out where I'm going to do that. So let me kind of give a pictorial representation of what I just said. Oops. Let's look at that. Seventh order polynomial. We can consider to use a higher order poly where transitions occur I have no idea why my eraser does not want me to erase free. Must be. And a low order polynomial during constant motion. So we can account for the discontinuities, or we can account for smooth motion at discontinuity. This is really frustrating. Discontinuities by higher order polys and low order poly one that's having fun today, all I can say. Elsewhere. Won't even let me screen it. I think I know what's wrong. Is that it's not connected to the internet right now, and I have to reboot to do that, and it's like that's what's going on. Okay. So the idea is this. I could look at, say, a fifth order polynomial. So here, I'm starting here at 0, right? And a straight line might have me something like this. What I would do is take maybe a fifth order to describe this motion, a fifth order to describe this order, and then maybe a fifth order to describe this one. I would do a third order for here and here. So that this would be a 5-3-5 kind of behavior. So this would be a waypoint and a waypoint. So far, so good. I'm debating on what I want to show you guys. I think I want to, before we go into the segmented motion profiles, I want to show you the complete MATLAB. So what I'm going to do, well, that's launching. So the idea, this notion here, this is considered segmented trajectory profiles. All right. Trajectory. On your exam, you're able to use MATLAB, but you have to show me the MATLAB code that works with it.
By showing you, you mean like when we submit it?
Yeah. So let me show you, before we jump into segmented trajectories, let's look at the example that we just did if we were to look at this in MATLAB. I'm going to show you two files, and you're literally going to see the example that we just got from time. So here we have a fifth order system. Here's our initial conditions, our initial our initial positions, our start and stop velocities, and our start and stop accelerations. We can goof around with this all day long. I'm going to give a duration of t final. Let's set to 5 seconds. Here is my theta vector, defined as theta init, theta dot init, theta double dot init, final, theta dot final, theta double dot final. This would be the M matrix that we saw before. So a square matrix, 6 by 6. And here's how we're solving for RC. So it's M inverse times theta. We get to check it just because I want to check it. And this becomes our time values for each one of these. So here is the position. This would be, it's getting a little confused. So here would be my position, my velocity, my acceleration, and my jerk. And then I'm going to plot each one of these, and then you can see what the maximum of this one is and the maximum of this one is by this max definition. Okay? So when we do that, when we run it, here's our values. And this would be the graph. Start with the min and max. I use this fraction here just so I can get a finer resolution. So I had to incorporate that into this time plot here, I. And just FYI on that. So that's the idea behind this. So T is the same. I'm fractionalizing it into I steps within T. But this little thing fixes it. Here you can see we're fractured right there. Right. So I'm iterating to 500, but I'm really going to 5. I'm going to 5 seconds. So that's really what we see T is 5 seconds. Don't get confused by that. Let's suppose we wanted to start at, give me another velocity, or you guys want to finish at a different velocity or position or acceleration?
25.
25 for what? Starting position, acceleration, what do you want? 25 then. And I'll give you guys this code.
Final.
Final what? Position?
Mm-hmm.
So you want to go from 30 to 25?
No.
Oh,
Okay.
you can do that, it'll work.
Okay.
Okay, I've never tried that one. It'd be kind of interesting. Then we click the run button. Okay, 5 seconds.
Wow.
There you go.
It's precious.
In fact, I think I need to clear that. So I had to hold on. Run. There you go.
Mm-hmm.
My acceleration started at 10 degrees per second squared, and I ended at 10 degrees per second squared, my initial velocity. And you can see the velocity is changing up and down. Now, I could say, let's go to minus 75. How about that? I haven't done that one before. Let's go ahead and say that we're going to end at a velocity of 5 degrees per second. And let's change our accelerations to be plus minus 5. Clear that graph. And run. There you go. So this is our starting position, our ending position. These are the motion profiles for velocity and acceleration. Pretty cool, right? The math we just did, nothing steep, but I simplified the computation by writing the MATLAB, right? Okay, is there any questions on that one so far? Pretty cool? Okay, let's kind of get a little more extravagant. How about that? Let's go ahead and do path and trajectory family. This one's kind of fun. Okay, so again, I have a fifth order polynomial. Again, the same M direct, this is the same M matrix. It's the same structure. If I go to a seventh, then obviously I'm going to have some more initial conditions, right? Because I'm going to have more things here. No big deal. And I need to be squared. That's why we're going in odd orders, by the way. You say, well, how come we're going odd? Because we need odd orders for that, but this particular solution. 535, 434 is not quite the same answer. So we run it. Let's go ahead and obviously I got to clear my graph, I think. Otherwise I'll get confused. Play, run, and then we're going to see. Yeah, change forward. We're going to see a couple of different things happen. What I've got here is what ifs. Here's my maximum acceleration as it changes and my maximum velocities as they change. But I have a family of plots right here for different possibilities. So let's see what the codes do. So again, here's my initial setup. My acceleration, though, is varying, changing, plus minus itself. Okay, Excel is going to be a 1 over j. So it's going through and finding, well, what if j is switched anywhere between 1 to 10 degrees per second squared? You all see that? So now I'm looking for a family, like I want to sweep across a set of accelerations. Zoom out. Depending on the acceleration that we see right here, it's going to give us different velocity profiles in different position trajectories. I can change, instead of it being up to 10, let's suppose we're going to give ourselves no more than 7 degrees per second squared. Let's go to minus 75. My final velocity is going to still be 0. So I want a 0 final velocity, I want a 0 initial velocity. Click the run button. Here are all the different parameter types I have here. Now I know that this is position. Then I have this guy right here is, let's see, what is that? Oh, I forgot to clear it, that's why. So wait a minute. There we go. So here is our position, velocity, and acceleration. Here's position. Here's velocity right here, 0. Comes down here, gets to that point, 0. And then this is my acceleration. So I can see what my acceleration is. So I can limit my acceleration for a sweep across, and I know I can't exceed it. What is that going to do to my velocities at any point in time? Does that make sense? So you can see, again, I'm only sweeping for all possibilities here. And then I go through here. I find my C's. And then I compute each one of the final values for the theta double dot, theta double dot, theta dot, theta, etc. And then I plot the family of each one. At the same time, I'm getting my maximum accelerations, my maximum velocities for each one. And instead of just giving out a single value, I can see for the given accelerations that I've got, what the maximum acceleration velocity is going to be.
And using a fifth order to define like.
This is a fifth order for defining the motion profile. If you want to do a seventh order, you just grow this to a seventh order. I can't remember if I asked you that on the exam or not. But you're more than welcome to use both of these files to support your exam. Okay. Want to see any more what ifs? Any other condition? We can go. Now it's time to ask because we're going to go into segment it after this.
Could we do the family trajectory one?
Okay.
And then for the initial conditions,
Yeah.
can it be from 0 just all the way to 6?
Well, that's a good question. Yeah, what would that do? It shouldn't do anything, right? And why would we actually not do that? Right. So what would we do in place of that? In place of that computation, if we were to do that to solve that solution for that inverse kinematics, what would we actually be doing? This is assuming position is represented as an instant, right? So we want to do one complete rotation. So we have to do 0 to 250 to 359. Right? We want to see one rotation. But let's go ahead. We can do that. So initial position is 0. We can go to 359. Actually, the math isn't going to care. Honestly. What do you want for the velocities?
Additions? Can they both be 5?
Sure. I mean, we're starting at 5 degrees per second, and we're ending at 5 degrees per second. We might want to know that when we do a 434 or a 535. I could do this same exact thing. I've given you the fifth order. You could make your own for a third order, where you take the output of one to the input of another, and take the output of that one into the input of another, right? Okay. So we have 5. So what's your input-output acceleration? Our initial acceleration is 0?
No. Our initial acceleration would be 10.
Okay. I don't know what 0 would do. We can find out.
And then our acceleration
Would you want to do, this is sweeping a family. So if we're not going to do a family, what's that? So this is like
the
a whole set
acceleration
of
is
possibilities.
1 and 7.
1 to 10, okay. So this is accel and minus accel. Okay. Yeah, we want to have a negative acceleration. If you have to come in from that landing, it's negative, it's a deceleration. I forgot to clear this graph, so let's go ahead and clear that and clear that too. Rerun it. There you go. So it's going to go 0 to 360. And then we see acceleration. And acceleration is fitting as a third order. So we get that takeoff and that landing. Does this make more sense to seeing the graphs? Now, we can come back over here. What if we wanted to have acceleration and acceleration right here? I've never done this. We can see what's going to happen. In fact, I need to, let me just clear all these graphs. I should have a statement that says clear graphs, please. Run. There you go. But notice, we started at 0 acceleration. Notice what kind of acceleration we're going to have. Quite a bit. Anything else? What if we want to end with 5? There you go. But what I want you to notice is the difference in the velocity. And what this does over here, it changes how it changes this. What if we said this? What if, let's see what, that's going to be kind of weird, but let's see what the numbers are. There you go. So that has a positive acceleration. It's accelerating through. So it puts this guy to the left, the 0 crossing over here to the left. Makes sense. And it's kind of cool when you don't, the reason I didn't clear the graph is so you could literally play games with, well, what if? Compare and contrast. How did it do before versus the other? Right. So what if I did a -5? Run it again, and then we can see how that superimposes on the other one. If I didn't run it, I have that's interesting. I only see 2. There we go. Here's our acceleration. And let's go ahead and put this at +1. There you go. We're looking at the yellow ones. Move this sign. That's the one +1 is 5. So what you're able to do with this is actually practice your homework. You can do this to help your homework. You definitely, I'm not going to modify it for you guys to do the blended segments. And we'll finish up blended segmentation on Wednesday. But you can see why we're doing blended segments. So we could literally take this profile and blend it in the other profile. But we need to find out at what point do we need to make that transition. And so what we're going to talk about on Wednesday is the blended segmentation. There's a process to go through in the book. I'm not even going to write it out. I used to write it out for you guys. I'm just going to show you where it's at and not waste you guys this time just copying something from the book. We'll just pull it up. Okay, it's life's a lot easier to do that. But what we're doing is we're saying, okay, my initial velocity from the transition point from one is now the other. I can actually use this program to find what those need to look like. and find out where my T's are so they line up where I need them to line up. Now you have to do that by trial and error using this program. I don't use it by the T's. We'll go through that in the example that we'll do on Wednesday. So we'll do a blended trajectory problem on Wednesday as an example. We'll go through the process of what it is, and we'll talk about the idea. But now I think you guys have the idea. So you're, instead of just doing one polynomial to do this whole thing, now we're doing a high order poly, a low order poly, or you can take off. For cruising, this is low order poly. Come in for that landing as a high order poly. Does this make sense? I'm going to give you guys your homework problems for this class. I'm going to go ahead and submit everything. What I'm going to ask you guys to do for the homework is submit it all in one in a package in one submission. It's going to be called homework submissions, and I'll give you the other one for the simulation submission. Does that make sense? There's no point in having all these submission links for homework. It's just going to say part 2 or second half homeworks, but you just keep them. It's going to be a take-home exam. It's going to be very straightforward. We have some simulations to go with it. I decided not to give you guys the extra credit homework or extra credit simulations because I know how busy you are. Yeah.
Will the simulation involve us building a robot or using one that's already programmed in?
Probably the latter. Yeah. I'm not going to ask you guys to do a lot of work in this. I may say maybe using your Simulation 2 robot that you've already done, right? And I was having problems with the simulations showing up on publishing. Did you guys get the grades yet? Okay. I'm not letting Canvas eat your homework. That's what I'm trying to be very careful. I had that happen before, and I don't want Canvas eating it, so that's why I might create a new file and just post it for you guys from my Excel sheet, if that's okay. I was playing around with it. I talked to some students last week, and they said, yeah, it didn't work. I'm like, all right, so I tried something else, hoping you guys could see your... There's one more thing I can try. I hate Canvas. I hate Canvas. Okay, but does this make sense? Okay. That's about it. We got one more lecture. Wednesday, there's no lab.